Great, let's have a look at this problem. It's a problem that we've seen before. We've done the two-sample z-test for proportions. We've done the risk difference, relative risk and odds ratio with this exact same data. But now we're going to do Pearson's chi-squared test, or the chi-squared test for association, or the chi-squared test for independence. And we would use it as if we have more than two variables that are more than just two categories. So more than just two binary variables. But in this instance, we do have two binary variables. So let's have a look at the problem. Again, researchers randomly select 242 subjects from a population of people in care facilities. A random proportion of subjects are veterans and a random number have sleep disorders. So these are two binary variables. The researchers want to test the claim that the risk of sleep disorder is different in veterans compared to non-veterans. They have a total of 77 veterans that had a sleep disorder, 45 did not. 35 non-veterans that had a sleep disorder and 85 did not. And we have to use Pearson's chi-squared test to determine if there's an association between veteran status and sleep disorder. So let's have a look at what we can do with this test. We're going to do our 7 steps again. And first of all, we're going to start with the population parameters of interest. So let's grab our pen and we're going to have step number 0. Now you can do step number 1, I should say. You can do this in various ways. I think a nice way to do it when it comes to the fact that we just have two binary variables, meaning that if I express two of them, the other two, are in fact already expressed. So what we can just express is the probability of disease given exposure, once again, and the probability of disease without exposure. So you have to write this out in the exam. In words, you're going to say the proportion of veterans with sleep disorder and the proportion of non-veterans with sleep disorder, or the probability of a sleep disorder in veterans compared to the probability of sleep disorder in the non-veterans. If you have more than two categories, you would have to express all of there's going to be more. Say you've got 3 and 3, that'll be 9. You've got to express all 9 joint probabilities. And remember, probability, proportion, risk, these are all synonyms with each other. And so you'll have to express all 9. But because I have 4, if I express 2 of them, the other 2 automatically drop out from those 2. So that's all we have to state for the population parameters. When we look at step 2 for the null and alternative hypothesis, you can very simply state that veteran status and sleep disorder are not associated with each other. And for the alternative hypothesis, you just say that those two are associated. What are the measures of association that we have? Well, we have risk difference. So you could also say that the risk difference is 0. We also have relative risk, so you can say the relative risk is 1. And we also have odds ratios. You can say the odds ratio is 1. That's what it means to be associated or not associated. But in an exam, it's very, very good just to state that what we're trying to show is association between these two variables, veteran status and sleep disorder, and to say that they're not associated. The alternative hypothesis are that they are associated. When we use the two-sample z-test for proportion, we just use the risk difference. Under the null hypothesis, the risk difference is 0. And if you just work on those 3 measures of association, you can just use the confidence intervals to also decide between a null and alternative hypothesis. So step number 3, these things are all the same. So step number 3, we're going to say alpha equals 0.05. That's what we were told. Step number 4, we're going to use the chi-square test for association. Remember, there's many names, same test. And so what do we need? We need 2 categorical variables. We do have that. We are going to assume that all these observations are independent of each other, and that they're randomly selected. What we really do need is for, if we look at the D there, the disease, let's make that D and D bar, that those are actually random. But what we really want to look at is the expected values. There's a big smudge there. So let's just calculate these expected values. And remember how to calculate expected values under the null hypothesis. So let's put it right there. I'm going to say that was our contingency table, a table of observed data. Let's look at the expected data under the null hypothesis. What would I expect if I have 242 people and I expect that these 2 variables are independent of each other? Remember how easy that was to do? I'm going to look at all 4 of these. Now, in a lecture, we'll show that we use the multiplicative law of probability and say that if events A and B are independent of each other, then the probability of A and B equals the probability of A, probability of B. And if you use that derivation, the calculation actually becomes very simple. So we're going to look at row 1, column 1. So there's row 1, column 1. I observe 77. That's my joint frequency. What would it be under the null hypothesis? Well, it's its row total, which is 122. So I'm going to have 122 times its column total, which is 112, divided by the sum total, 242. That is going to be the expected value. 77 is observed. This is what I would expect. Let's go to 45. I observe 45. What would I expect? Well, it's its row total, which is 122, multiplied by its column total, which is 130. And I divide that by 242 once again. I go to the observed 35. Its row total is 120. So this is going to be 120 times its column total is 112, divided by sum total, 242. We go to observed, which is 85. What would I expect? Well, it's a 120, the row total, times the column total, 130, divided by 242. And there I have my expected data. Now we just have to calculate those. And so I'm going to check my calculator. You see if you get the same results. I get the following: 56.45, 65.55, 55.45, and 64.45. And now look what I have. Let's take the orange again. I have here my observed, oh, that's the wrong color. Observed 1, 1. My observed row 1, column 2. Observed row 2, column 1. Observed row 2, column 2. And if I had more, we just carry on with that. This is my expected row 1, column 1, my expected row 1, column 2, my expected row 2, column 1, my expected row 2, column 2. So there I have my observed data and my expected data. Look at this. As far as the assumptions for the use of this test is concerned, I need all of these values, at least 80%, but I only have 4, so it's got to be all 4 of them, have to be 5 or more. And we do have 5 or more, so that's fine. The only thing that we still have to do, remember, is we have to calculate the degrees of freedom. So the degrees of freedom is going to be the number of rows minus 1 and the number of columns minus 1. That just means how many categories in my exposure variable, how many categories in my outcome variable. Well, I've got 2. 2 minus 1 is 1. 2 minus 1 is 1. 1 times 1 is 1. So in this instance, my degrees of freedom is going to be very simple. That's going to be 1. So what we're going to have is we're going to calculate an x squared statistic. It's going to be described by the chi-square distribution on a single degree of freedom under the null hypothesis. That's what we're going to have. So let's see in step number 4, and step number 5, let's actually calculate this x squared statistic. So there's step number 5. And let's write that in green. So remember, x squared is going to be the sum from I equals 1 to the number of rows, and the sum of j equals 1 to the number of columns of observed ij minus expected ij squared. And I'm going to divide that by expected ij. And under the null hypothesis, remember, that's going to be described by the chi-square distribution on a single degree of freedom. So if I were to do my study over and over again with those two variables independent of each other, I'm going to get a bunch of x squared values, and their theoretical distribution is going to look like this. So let's write all of this out and calculate that. So I'm going to have that x squared equals, now I have to go back to a previous page, so let's have a look at that. Observed minus expected. So observed is 77 minus, so observe minus 56.45, 56.45 squared divided by 56.45 plus, and the ij just means go through row 1, all the columns, then jump to row 2, all the columns. So the next one's going to be that one. 45 is my observed, minus expected is my 65.55. I square that and I divide by 65.55. I go to the next one. My observed is, so I've done with the first row, go to the second row, 35. That's what I observe. Minus what did I expect? 55.45. I square that and I divide by the expected 55.45 plus the final one I observed 85 minus what did I expect 64.45. I square that and I divide by what I expect 64.45. So those two are the same, those two are the same, those two are the same, those two are the same. Great, let's get our trusty, let's smear some more. This ink is really going for me today. I'm not being careful enough. It's actually horrible. And anyway, I like my fountain pen, so we have to live with it. And if I sum over all of those, I get a very large number, 28.01. 28.01. That is very big because in step number 6, I have to do a critical value. Step number 6, I've got to get a critical value. And that critical value, remember, that's going to be 1 minus alpha for a single degree of freedom. And so if you get that in your spreadsheet, that's going to be 3.841, 841. That's our critical value. And of course, here we have that now our 28.1 is way bigger. That's going to be a very rare, that's in really far out in the region of rejection. That is not a very probable value to get, or it's at least in the region of the 5% least probable x squared values. And so we reject the null hypothesis, and accept the alternative hypothesis. So let's write step number 7. So I've simply written there's enough evidence in the data at the 5% level of significance to show that veteran status and sleep disorder, those two variables are associated with each other. So if you have a look at all the videos in this series, you'll see we've done a chi-square test, we've done a two-sample z-test for proportions, and we did all 3 measures of association, 3 different problems with the same data, with this exact same data, and through all of those we came to the same conclusion, that there's an association between these variables, and there's various ways to solve this problem. So let's have a look at what ChatGPT, look at I've got O3 mini high there, I've typed in my problem. I do start the prompt. Remember that I put a link to the prompt, or just at least copy and paste the prompt down in the description. And I say, help me with the following biostatistics problem. I paste the problem in, and I also say, generate the solution based on our 7 steps. And I write the 7 steps out. Let's have a look at that. It says my population parameters there. You can have a read and pause. You can read the null and alternative hypothesis. Slightly different as the way we stated it, but it means exactly the same thing. Our level of significance being 5%. Our statistical test and assumptions, we can use Pearson's chi-square test of independence. The data consists of counts, frequencies from a random sample. These are all independent of each other, and the expected cell counts in the contingency table should be sufficiently large, so we need at least 5. So to calculate the test statistic, look at that. That's our contingency table, or our table of observed data. And now it tells us how to calculate these expected values. Row total times column total divided by sum total, or grand total is what it calls it. So there are my 4 cells. So row total times column total divided by sum total, and I see the 4 expected values, and all 4 of them are 5 or more, so I have no problem there. It's calculating the x squared statistic. It's a bit lazy in the way that it states it. It doesn't do over the rows and the columns, but the point comes across. We always want observed minus expected, squared divided by expected, and that's what you see there. So the first one was 77 minus 56.45 squared divided by 56.45. And the next one is 45 minus 65.55 squared over 65.55 squared. So the corresponding observed minus expected squared. And I get a test statistic of 28.01. We can see the degrees of freedom, 1 degree of freedom. And that means we have a critical value of 3.841, as we can see there. And our test statistic is much larger than that. So we reject the null hypothesis. We can see the conclusion there, pretty much as we stated. And then I also said create some code for plot. So let's copy and paste this code. I'm going to copy this code, and I've pasted into a Jupyter notebook. Remember, that's just available to you freely, just together with your Google Doc and Google Sheets. It's right there. And look at that. There's our chi-square distribution on a single degree of freedom. We see tiny down there our 5% least probable x squared values from 3.841 onwards. And our test statistic was so big it doesn't even fit on this plot. So clearly in the region of rejection.